We're just starting this fish problem. Trying to. 1 second. Yay, finally success. Okay. So maximum length of 29 centimeters. The growth model predicts that the growth rate, I'm just gonna say the growth rate is 25 e to the negative a centimeters per year, where a is the age of the fish. Find the average length of the fish over the first 5 years of life. Now, one point I'll make here, and this is the, let me turn this on. One thing I find annoying about this problem is they use A when we always use T for time, but they're using A for time here or A for age. So A is the variable, not T. Oh well. The thing that's actually more confusing here is that it's really, really easy to go the wrong way with this problem because you might just think, okay, average value, there's that function. I'm going to integrate that function from 0 to 5 and then divide by 5 minus 0. And that would be great if they gave us the function that was representing the length of the fish. Right? If I want to find the average length of the fish, I integrate the length function and divide by the interval. But they didn't give me the length function. They gave me the growth rate or the rate of change or the derivative of the length function. So what they actually gave us was L prime of A, which is 25 e to the negative A. And to find the average value is going to be 1 divided by 5 minus 0 times the integral from 0 to 5 of your actual length function, which we don't know yet. So this problem is actually going to require essentially anti-differentiating twice. We're going to have to anti-differentiate this derivative to find the length function, and then do this process over here to find the average value. So it just goes to show how important reading the words in the question are. If you just kind of glanced over this and saw, oh, there's a function, average value, I'm going to integrate and divide, we would end up with the wrong answer. So let's find our length function by anti-differentiating this. So the length function is going to equal the antiderivative of 25 e to the negative a, which is going to be 25 e to the negative a divided by negative 1 plus c. That's the length at any age a. I would probably rewrite this as negative 25 e to the negative a plus c. But we need to know what c is so that we can then, whatever this function is, that's what's actually going to go into the average value there. Well, we have some more information. We know that at the start of life, when the age is 0, the length of the fish is 4 centimeters. So we know that L of 0 should equal, well, is equal to negative 25 times e to the 0 plus c, and that should equal 4. E to the 0 is 1. So if I add 25 to both sides, I'm going to get c equal to 4 plus 25, which is 29. So this function is actually negative 25 e to the negative a plus 29. What's interesting here, I think, before we finish the problem is they gave us another piece of information which might seem superfluous, extra, like we don't really need it. And that's kind of true. This piece over here, that the max length of the fish is 29 centimeters, we don't really need to finish this problem, but it is worth noting that if this is our function, we shouldn't be able to exceed 29 centimeters. And that's true. If you let a go from anywhere from 0 to infinity, this value here will be always smaller than or equal to, I should say, bigger than or equal to 0, right? Whatever this is here, less than or equal to 0, right? This e to the negative a is always positive, multiplied by negative 25, it's going to be negative always. And the negative number plus 29 is always going to be less than 29. I think a better way of saying that would have been to said, if you take the limit as a goes to infinity, the length of the fish gets closer and closer to 29 centimeters. You let the limit, just a goes to infinity of negative 25 over e to the a. It's a nicer way to write that. That part's going to go to 0, and you're going to get 29. So if the fish lived forever and it continued to follow this model of growth, it would get closer and closer and closer to 29 centimeters. Not really the meaning behind it, but it's kind of what you can say. All right, but let's actually finish the problem. What we really wanted to do is calculate the average value. So our average value, or our average length, is going to equal 1 over 5 times the integral from 0 to 5 of our function, which is exactly this. Negative 25 e to the negative a plus 29 dA. And the rest of that's not too terrible. We're going to integrate this. We're going to get 1/5 times, let's see, the integral of negative 25 e to the negative a is negative 25 e to the negative a divided by negative 1, or let's just say positive 25 e to the negative a. Plus the integral of a constant is the constant times the variable, evaluated from 0 to 5. Plugging in, we get 1/5 times 25e to the negative 5th plus 29 times 5 minus 25 times e to the 0, which is just 25, plus 29 times 0, which is just 0. This ends up equaling 1/5 times, let's see, 29 times 5 minus 25 is going to be something like, I don't know, 145 minus 25 is 120. And then we have this part here, plus 25e to the negative 5th. It's approximately 24.03 centimeters. It grows pretty fast, right? If it starts at 4 centimeters and gets to a maximum of 29 centimeters over its entire lifetime, in the first 5 years, the average length of the fish is 24 centimeters. It's growing pretty fast. Interesting. So again, I want to reemphasize here the importance of making sure you read the words in the question, right? Because they tell us more sometimes than we really realize. I got you. Oh, here you go. So it's important to read the words. It's important to scan the words to make sure you're looking for the things that matter. All right, let's go ahead and start something new. Yeah, and maybe next time we'll talk about a different survival renewal question, but I would like us to start talking about volume because volume can be a little bit confusing. So let's talk about volumes of solids. And for the most part, we're going to be talking about volumes of revolution. And I'll ask you all to pay attention in your class. Neither of your instructors should talk about the shell method. If they do, let me know. Sometimes Dedell is known for doing more than is really necessary. So if Dedell specifically mentions the shell method, let me know and we will talk about it. But I don't expect them to because it's not in the syllabus with the class at all. Yeah. So let's look at this example. We're going to find the volume of the solid formed when the region bounded by f of x equal to x cubed, y equal to 0, and x equal to 2 is revolved around the x-axis. And this is definitely a place where your graphing skills are important. I think, although there are ways of doing these problems without graphing the region, the fastest, easiest way to do these problems is by graphing the region that's described. You don't have to be able to draw the 3D shape, but you need to be able to draw the region that's going to get revolved around whatever axis we're revolving around. So let me read this because I see some people not seeing all the words I'm writing. find the volume of the solid, that's a D in case you were curious, formed, yeah, I was going a little too fast there, when the region bounded by f of x equal to x cubed, y equal to 0, and x equal to 2 is revolved around the x-axis. So I'm going to draw my region. So f of x equals x cubed. I don't really care about this part over here, but I'm still going to draw it. So here's the part of x cubed I really care about. And then y equals 0 is the x-axis. And then x equals 2 is a vertical line. Looks something like that. So here's the region that we're then going to revolve or sweep around the x-axis to get some solid three-dimensional shape. And the idea is, in fact, I am going to draw the picture here, although I don't think you need to draw these pictures in general. I want to show you. So the idea is you're going to take this region and then revolve it around the x-axis. So it's going to kind of reflect along the x-axis and look like this. Kind of like that. And what we're going to do is we're going to take essentially a little slice of this solid and find the volume of that slice. And then just like when we're finding area by adding up a bunch of rectangles, we're going to find volume by adding up a bunch of slices. Just like when all the rectangles had different areas, we had to kind of find a general formula for the area of each rectangle. We're going to have to find a general formula for the volume of each slice. Fortunately, those slices have a pretty nice shape. These slices, so this slice here, I'm going to draw it bigger over here. So there's my slice. And my slice is a cylinder. It's a really, really flat cylinder, right? It's got almost no width, but it is a cylinder. And this cylinder has some radius, and the volume of this slice is going to be the area of that circle times its thickness, its height if you turn it on its side. So it's going to be area times thickness, which in this case is the area of that circle is pi times whatever the radius squared is. By the way, the radius is going to change, right? If you go way, way left in this solid, the radius is really small. If you go all the way to the right, the radius is really big. So that's the part that's going to be variable. And the thickness is a very, very, very small change in x, right? You've got some little motion in x here. So our thickness is going to be dx. You could say delta x if you wanted to. I'd say dx because I know this is going to go in an integral. So what's the radius of our circle? Well, it depends on what point we pick. So let's use a different color here. If we drew our little rectangle that gets revolved around the axis to form a disk like this, then we're going to think of this rectangle as being x away from the origin. And the height of that rectangle, which is the radius of this disk that's a slice, is just whatever the function is. So here, my radius is going to be x cubed. For this slice that's located x away from the origin. Sorry. If you need me to move things up, please let me know. I get stuck in this corner down here sometimes. That's the volume of that slice. Question. So I'm thinking, I know my picture is not wonderful here. I'm thinking of taking this little rectangle that I drew right here and revolving it around the axis. So this length here, that height of the function is the radius of this disk. And so, right, if I pick this smaller piece over here, right? That little disk would have a much smaller radius because the x value I'm picking is smaller and x cubed is going to be smaller. So I like to think about the radius being essentially how far away we are from the axis of rotation. And in most nice cases, it's going to be your function. It'll get more complicated, but for now, the function. But that's just the volume of one of the slices. I want to add up all the volumes of all the slices. And just like we add up all the areas of the rectangles to get the total area, we add up all the volumes of the slices by using an integral. So the total volume here is going to equal, we're adding up, we're integrating from how far left could I draw a rectangle? 0. I mean, it'd be a real super short rectangle, but you can go all the way far, or really, I should say, how far left can you go in your region? As far left as 0. How far to the right? 2. Those are our limits of integration. We're adding up all the slices from as far left as 0 to as far right as 2. And then our function, sorry, the volume of our slice is pi times x cubed squared. Most people immediately put the pi out in front of the integral. So we've got pi times the integral from 0 to 2. X cubed squared is x to the 6th. It's a pretty straightforward integration. We're going to get pi times x to the 7th over 7 from 0 to 2. And we plug in, you get pi times 2 to the 7th over 7 is 128 over 7 minus 0. So we end up with a volume of 128 pi over 7. And honestly, the setup part is the more important part. The actual evaluation of the integral, although often worth some points, is usually the less important part. They want to see that you can set these up. Your teachers are less kind of concerned with your ability to actually evaluate them. And in fact, it's very likely that at least one of your next exam questions will be a problem where it's like, set up this integral and do not evaluate it. So make sure on your next exam, especially when you get to the volumes part, you're reading the instructions very carefully so that you don't do more work than you actually need to do. So this method of integration or finding the volume of a solid of revolution is called the disk method because we're adding up volumes of disks. And how do I want to say this next part? I don't really want to do this other example here like this. We'll come back to that one. So let's look at a different, we got time. We're going to come back to this region, but not quite yet because I want to show you something else first. So let's look at a different region. Let me go back here. So same idea. New region. It's going to be the region bounded by, sure, y equal to x squared and y equal to 3x. And we're still going to revolve it around the x-axis. We're going to find the volume. So I'm going to draw my region. So I've had a lot of practice doing this, not surprisingly. I know what my region is going to look like before I even start drawing it. But if I didn't already know, I would probably, or should probably start off by finding where these two functions intersect each other, because that's going to help tell me what the region is. So see if you only have two curves, like the previous example, there were 3 curves, so we kind of just drew them. Here, I'm going to find where these intersect. So I set x squared equal to 3x. Don't divide both sides by x. Bring 3x over to the left, and then factor out an x, and get x times x minus 3 equal to 0. So we know that these intersect at x equal to 0 and x equal to 3. I know what they look like. One's a parabola, typical, usual parabola that goes to the origin at the vertex. And the other one is a straight line with a slope of 3. My slope probably isn't quite 3. Oops, wow. Oops, okay. Got all cocky about my drawing skills before I started drawing it. So there's the point of intersection where x is 3, and if x is 3, y is 9. And here's the other point, 0, 0. I really just wanted to draw this way. So I didn't need, and you don't really want to draw all the extra parts of the graphs here. So a better picture, a more helpful picture, would have been to have just drawn the part I kind of care about. And maybe exaggerated a bit so I can make my drawings easier to see. Okay, so we are using the shell method. The shell method. We are not using the shell method. Oh my God. We're using the disk method in the last example. Here we're going to use a method that's essentially the same, but it's called the washer method. You'll see why in a second. But here's what I want to actually say. Whenever you're finding the volume for a volume of a revolution, you're going to draw a little vertical or horizontal strip. And the way you know the orientation of your strip is it should always be perpendicular to the axis of rotation. So if your axis of rotation is the x-axis, you should be drawing a vertical strip. And in the second, if your axis of rotation is the y-axis, you're going to be drawing a horizontal strip. We'll see kind of that in action here. So here's the little strip I'm going to draw. And I don't really want to draw the 3D shape here. It's not super helpful. But what I do want to do is draw what happens if I revolve this little strip around that axis. Well, check it out. If we revolve that strip around that axis, we're going to be missing some stuff in the middle. I have this shape here. That kind of looks like a disk, except I pulled out an inner disk, or also known as a washer. So if I take this rectangle and revolve it around, right, like I've got like my rectangle here, my axis here, and I revolve it all the way around, I'm never touching the middle. So I've got this hole in the middle. So the volume of this washer is going to be very generically the area of the bigger circle. In fact, let me label some things here a second. So I'm thinking of this distance as the larger radius and this distance as the smaller radius. So my volume of my washer is going to be the area of the larger circle, pi times big R squared, minus the area of the smaller circle, pi times little r squared. All of that multiplied by the thickness of the washer, which is still dx, or delta x, if you like. The only real difference between this example and the previous example is that in the previous example, the inner radius was 0. So we didn't even think about it. In this example, the inner radius is not 0, right? This function, I should say, this region, I guess I should draw it, even though I'm not great at drawing this. If I revolve that region around the x-axis, you don't need to draw this. I do need to draw it. It's going to look kind of weird. It kind of looks like you can't really kind of see it for the most part because you're kind of cutting out that part right there. See if I make my picture any better. Yeah, this picture just does not want to be nice really ever. And so my washer kind of does this deal. You can kind of see what's going on there, kind of. I kind of think of it, it's been a while, but have any of you ever seen those, like, when people used to go to malls, there were these things you would put coins in, they like spin around, 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 and go in the middle. It kind of looks like that, like where you have like that kind of black hole kind of shape, but it's like to the side. So that's what I imagine that kind of looks like. You've got this cone and you've kind of scooped out this inner part. We don't need that picture to find the volume here. All we need to do is add up all of our volumes. So we're just going to add up all the volumes of the washers. Oh, I should point out what the outer and the inner functions are. So the outer radius is the function that's further away from the axis of rotation. So in this case, our outer radius is going to be the further away function, which is 3x. Our inner radius is the function that's closer to the axis, which is x squared. Another reason why it's really good to draw the picture, because drawing the picture, you can just look at it and see which function is closer, which function is further away. So the volume in total, we're going to add up, integrate all of the volumes of the washers. So I'm going to wait on that for a second. All the way from as far left as x equal to 0 to as far right as x equal to 3. And we're going to be integrating. Now, I would factor out the pi and write it as pi times 3x squared minus x squared squared dx. That's our volume. Yes, we can calculate it. It's going to be pi times the integral from 0 to 3 of 9x squared minus x to the fourth. And then we're going to integrate. We're going to get pi times 9x cubed over 3 minus x to the fifth over 5 from 0 to 3. And when you plug in 3, you're going to get pi times 9 times 27 over 3 minus 3 to the fifth over 3. Minus 0, minus 0. And you could simplify this, but I don't really care so much about that. I care about the fact that we can do it. So here's what I would point out. This region, there's a gap between the region and the axis of rotation. And when there's a gap like that, you're going to have to use the washer method because there's an outer function or an outer radius and an inner function or an inner radius. Whereas in the previous example, this region, there wasn't a gap. That region is flush with your axis of rotation, meaning you're going to use the disk method, or there isn't an inner radius, or the inner radius is 0. Another way to say that is the axis of rotation is one of your boundaries. And it was, right? Y equals 0, the x-axis, oh, you can see that. Y equals 0, the x-axis was one of our boundaries. So if your axis of rotation is one of your boundaries, that's almost always going to mean you're using the disk method. If it isn't, washer method. And what I really, really want to say is they're kind of the same method. It's just one of them has an extra little piece. Do I have enough time? Maybe. So let's do one more. Let's go back to our original region, but now we're going to revolve it around the y-axis. So original region revolved around the y-axis. I'll remind you, in case you're not looking at your notes like I am, our original region was the one bounded by y equals x cubed, x equals 2, and y equals 0. So now, when we revolve this around the y-axis, well, our axis of rotation is vertical, so our strip or a rectangle had better be horizontal. So this is my horizontal strip, and I'm going to revolve that around. I like to do it like this. Again, you probably don't have to draw this picture, but I need to draw it so you can see what I mean. So there's the washer that we're going to find the volume of. And just like last time, I have an outer radius and an inner radius. And the volume of my washer is going to equal, I'm going to factor out the pi this time, pi times the bigger radius squared minus pi times the smaller radius squared times the thickness of the washer, which is dy, a small change in y, not a small change in x. So here's the problem. When we find this volume, when we add up all the volumes of these washers, we're going to have an integral, and the variable is going to have to be y because we've got a dy, not a dx. Right? The d whatever, the differential, that tells you what variable you're integrating with respect to. If you've got a dy, you have to have your functions written as functions of y, not functions of x. So it would be incorrect to say that our outer radius was 2. Well, that's correct. And our inner radius was x cubed. Because when we do that, that's going to be a problem to integrate. So instead, we have to take the y equal to x cubed and solve for x and rewrite it as x equal to the cube root of y, or y to the 1/3. So then the actual volume of our washer is going to be pi times your big radius squared, which is x equal to 2, minus your small radius squared, which is x equal to y to the 1/3 squared dy. That's the volume of that washer. And then to find the total volume, oops, we're out of time. We're going to add up all the washers. We're going to go pi integral of 2 squared minus y to the 1/3 squared dy. And my limits of integration are different. Before, they were left x equal to 0 to a right value of x equal to 2. Now they're going to be down as low as y equal to 0 to up as high as, if x is 2, y is 2 cubed, which is 8. So our limits of integration have to be y values, not x values. And here, now, I still think saying the function further away from the axis is your outer radius, the function closer to your axis is your inner radius. I definitely recommend drawing these every time because you're going to see what's what. The last thing I'll say is this is pi integral from 0 to 8 of 4 minus y to the 2/3. And then integrating this is not that. We'll talk more about this on whatever next Friday, the next day we meet. Next time.